Hello, welcome to the AdSim++ instruction video called Inputs and Outputs. My name is Nico Punt and I will show you today what you can do with the input and output objects which are part of the PKPD library of AdSim. Okay, well up to now we used models like this. We had a compartment and we connected a sync compartment to this compartment, and we introduced material into this model by setting the initial amount in this compartment. And if I click run, I see here how the material flows from this compartment to that compartment. And well, we can see this as an elimination from this central compartment. And I can replace this with an output, because it does exactly the same thing. So if I delete this, I drag an output right here, and I connect them. And this is simply a linear output, T elimination. And if I simulate again, I get exactly the same curve. So now back how we introduce material into this compartment. If I double click here, I did this by setting the initial amount, but that's not that very flexible because it's only at one time point, time 0, and only one dose, in this case 100 milligrams. So that's not very flexible. And that's why we created so-called input objects to make this adding of material into a compartment more flexible. So I reset this to 0, simulate again, so there's no material, and now I will add an input. And I connect it right here. And I do a simulation and see a very nice repeated injection profile. And if I click here and I look at the object level, you see where the schedule is defined. So 100 milligram starting at time 0 with an interval time of 8 hours and 10 dosages. Well, and this scheduling is extremely flexible. You can have multiple sequences that can overlap, for instance. And I can give a demonstration. I can change this regular schedule into a day-night rhythm. So what I could do is say, okay, I give this 100 milligram every 24 hours. And I give them, let's say, 3 dosages. And I give another 100 milligram at 6 hours thereafter, and also an interval time of 24 hours and 3 dosages. And the last 100 milligrams I give at 12 hours, so it's let's say dinner time, and also 24 hours, 3 dosages. And if I simulate this, you get a very nice day-night rhythm. Okay, I will delete these lines here. I will restore the original interval time of 8 hours. I give 10 dosages again. But now I will start at 48 hours. So if I simulate this, you see here, initially nothing happens, and after 48 hours the schedule is kicked in. Now what I can do is, and I'll move this a little bit here, I can simply add another output to the same compartment. Sorry, input to the same compartment. And this time I will select an infusion input. And I connect it like this. Okay, let's define the schedule. So for the infusion input, I say, okay, I'm going to give 100 milligram right from the start for a duration of 72 hours. So what you give is 100 milligram over a period of 72 hours. So it's one continuous infusion. And let's have a look how this looks like. So here you see the infusion, and then on top of that the other schedule starting. Let's go up a bit with the dose. Let's make this 1000. So it's even more clear. So here's the infusion, and here is the injection schedule, and here they overlap. I can also add extravascular dosages. So if I add another input, and this time I select an absorption. Again, I connect it here to this compartment, and I say, okay, I'm going to give here, for instance, 200 milligrams, starting at 130 hours, with an interval time of 24 hours and a total of 4 dosages. So if I simulate this, and look here at the big screen, you can see there is even some overlap here, and then you have your oral only regimen. So this demonstrates the incredible flexibility of this dosage scheduling at Sim++. So we're now going to take a closer look at the different input types. I create a very simple model with an input into a compartment, and we will not attach an output, just an input, and so that the material can accumulate in this compartment. We adjust the dosing schedule, we just give a single dose. Okay, and if I simulate this, it's typical for an injection. Just 100 goes in very quickly. So this is the injection profile. Now let's make a copy. And now we will select here a infusion. Let's take an infusion. And the infusion duration we set to, let's say, 8 hours. And let's do a simulation. So this is typical for a infusion here. It's a zero order input, and here the infusion stops. Okay, let's continue. Let's make another duplicate. And we'll select an absorption, the first order absorption input. And we change the absorption rate to 0.25, which gives some nice results we can view here. Now if I simulate this, something interesting happens. It looks like if the absorption stops at a certain time point. Now if I look here in the results, yes, we can see that the absorption stops suddenly at 8 hours. And I can explain that if I click here and look on the scheduling. You can see there is a duration set for the absorption. It's normally used for infusions to specify the infusion time, but you can also use it for absorptions. And then the absorption will stop after 8 hours. If I put here 0, the absorption simply continues, and if I simulate again, then you get the normal profile, and so here you have your well-known first order absorption profile. Okay, now let's continue to some more exotic inputs, and the first one will be the so-called Weibull input. So I make a copy again, and I select here the Weibull input. So, and the Weibull input is in fact just a kind of distribution function, which has two parameters. It's this is so-called shape factor and time factor. Okay, let's simulate the default values first. So here you see the profile. Now, if I can increase the time factor, for instance, to 5, and you see it slowly going to the right, or 8. And if I change the shape factor, for instance, I double it to 2. You look here, you see the shape change. Double it again. So this is quite a different profile. So if I look here, you can see here the Weibull input. So this is kind of general purpose input. For instance, you could use it if you have in vitro dissolution data of a tablet or other preparation. You could fit those data and then use the Weibull inputs in actual human models. We have another distribution model, in distribution input, called the gamma input. Let's make a copy. I will select gamma here. Double click. So the gamma has also two important parameters. First is the transport rate, and the second is the number of compartments. What the gamma function, distribution function, essentially models is a number of transit compartments before it's actually entering your target compartment. Now here it's set to 1, and if I do a simulation, then you have a curve that looks like this. But of course I can increase the number of compartments. For instance, I can set it to 4 transit compartments, and then you see it's shifting to the right again. Or even 8 transit compartments, and look how it shifts to the right again. And if I make the absorption a little bit slower, for instance half, you get this type of pattern. So if I look here, so here we see now the different types of input profiles. So the 5 basic input types SIM++ currently supports. But this may be expanded in the future, of course. Okay, let's move on now to the different types of output objects. I will start with creating a simple model. I have a central compartment. I add an input here, and if I simulate this, I get this type of pattern. Now, because I don't have an output yet, so what I will do now is I connect here a peripheral compartment, and I will add a virtual compartment. And I'm going to make sure that I can see the concentration in this virtual compartment. Now simulate this. Okay, so this is the pattern you get now, and it's only accumulating because we did not add yet an output. So let's start with the most common output, just a simple first order linear output called T-elimination. I connect it, and I can simulate it now. And then you would get what we would expect. Now what I can also do is add an output to a peripheral compartment. So I add another output. And connect it here. So material is also eliminated from the peripheral compartment. As you can see. We can also eliminate, or virtually eliminate, from the virtual compartment. So I add another compartment, another output, and well, I cannot link these ones because a elimination output deals with real material. So we have to select here virtual elimination, and now I can connect it. And you'll see it if I do a simulation again. What happens here has no effect on what happens here, because as you know, the virtual compartments do not participate in the mass balance. So let's do a simulation again, and then we get elimination from the virtual compartments. So these are the basic, let's say, natural first order elimination types. So now we continue to the artificial output objects. And we have in SIM++ two types of artificial elimination. The first is hemodialysis, and the second is the peritoneal dialysis. And let me explain the difference between the two. With hemodialysis, we have an apparatus, and blood from the patient is moved into this apparatus. And the blood is then moved alongside a membrane. On the other side of the membrane, there's this dialysate fluid, which is moving in the opposite direction. And then here an exchange of drug is taking place. And then the blood is returned again to the venous system of the patient. So we model this as a first order elimination in SIM++. With a peritoneal dialysis, it goes differently. Then you have a bag with solution, and the solution is moved in the peritoneum of the patient. The fluid stays there for a number for a certain period, and during this period the blood vessels in the peritoneum and the fluid exchange drug. And after the completion of this period, the fluid is moved out again into the drainage bag. And as opposed to this hemodialysis, which we model as a first order elimination, we model this process as a distribution process. So now I will demonstrate the differences between these two types of artificial elimination. So I will start with a very simple model. In one compartment, I attach an output to it, and I simply say, okay, I have an initial amount of 100 milligrams. To do a simple experiment. And if I run this, you see that the output eliminates the amount. Now I'll change the output to a hemodialysis. And if I now run the simulation again, you see the full amount of 100 milligram remains in the compartment, because we have to activate the dialysis. So I can here go to the object, and what I will do, I will set a flow of 1 liter per hour. I start at 4 hours, and I will use a duration of 24 hours. And okay, this is it. So now if I run the simulation, you see here the effect. And an important parameter is here is the extraction ratio under constants, which is set to 0 or to 1. So I will change it to 0.5, and then we have a look at the effect here. See, it's moving that way a little bit. Okay, now let's duplicate this model. And we will change this to a peritoneal dialysis. Let's look at the schedule. So I look here. You see that I can here enter a volume. It's in fact back volume. And so I will enter here 1 for duration of 24 hours. It's effective, of course, but just a long duration. Okay. Now, if I simulate this, you get this figure. And now let's look here at the results, and I will add some grid lines to make it easier. Okay, so what you see here is that you have a redistribution. It's a distribution into this bag. And as you see here, the volume of the compartment is its default value, 1 liter. And the bags we are giving is also 1 liter. So you get let's say a dilution of 50%. And that's exactly what you see here. It goes from 100 milligram per liters down to 50 milligram per liters. So this is distribution. This is true elimination. And of course we can schedule these interventions. So for instance, the hemodialysis, I could say, okay, I want to do this for 4 hours with an interval time of 8 hours, and I repeat this 5 times. And I can do the same thing with the peritoneal dialysis. So say a duration of 4 hours, interval time 8 hours, and 5 times repeating. And let's see what this gives for results. And here you see the results. So this is, I think, a very nice demonstration, clearly demonstrating the principal differences between a hemodialysis and a peritoneal dialysis. So this concludes the video about inputs and outputs.